In this section, I'd like to cover 3 topics. The first one, given a language, construct an NFA that recognizes that language. The second one, given an NFA, possibly with epsilon transitions, convert the NFA to an equivalent DFA. And third, prove a closure property of regular languages. Let's start with the first one. Now we have a language. This language is the set of strings. Each string W contains at least 2 zeros or at least 2 ones. The alphabet is 0, 1. Now to do that, I can analyze the property of each string. We see there is an OR. That means I can separate this property into 2 properties. One is W contains at least 2 zeros. Another is W has exactly 2 ones. As we covered before, that we can construct union of 2 machines very easily with epsilon transitions. So why not do that here? We construct 2 machines that recognize each property. Then we combine that. We take the union of those 2 machines. First, let's consider the first property. W contains at least 2 zeros. So to construct a machine satisfying this property, I would like to do what I want. If I start from B, what I want is I need to read 2 zeros. So what I do, I read a 0, I go to that C, meaning that I have read 1 single 0. That's not enough. So I read another 0 and go to that D. That means I have read 2 zeros. Now the property is satisfied, so that D should be an accept state. Now I need to fill in the missing transitions. Now if I just have B, C, D and only 2 transitions, 0, 0, then I can only recognize the language which only contains 1 single string, 0, 0. So I need to fill in the other transitions so that I can accept other strings. For example, if I read 1 from state B, then I will stay at state B. That means I have read non-zeros. And if I'm at state C, I read a 1, I stay at C because I have only read 1 single 0. So reading a 1 doesn't change the state because only the number of zeros will matter here. And at last, if I have reached D, that means I have already satisfied the property, reading 2 zeros. Now I can read any number of zeros or ones. That's the machine that recognizes the language. W contains at least 2 zeros. Following the same strategy, we now construct the machine that recognizes the set of strings that contain exactly 2 ones. That is the bottom part of this machine. If I start from E, I need to read 2 ones. What I do is I read 1, 1 and go to that F. That means I have read exactly 1, 1 till now. Now I need to read another 1. So I will read 1 and go to that state G. Now I have read exactly 2 ones. So that G should be an accept state. Now I need to fill in the missing transitions. So if I'm at E, now only the number of ones will matter. So if I read a 0 from E, I will stay at E. Similarly, if I read a 0 from F, I will stay at F. The only difference is at G. At G, I have read exactly 2 ones. So if I read a 0 from G, I will stay at G. But I can't read any ones because I need exactly 2 ones. What I do is I don't add any transitions for 1. That means if I read a 1 from G, that branch of computation dies. So after constructing these two machines, I want to take the union. What I do is I add a new start state A and add epsilon transitions from A to the start state of each of the machine. So if you have 3 machines and you want to take the union of those 3 machines, you add epsilon transitions from the new state to the start state of each of the 3 machines. Alright, so that is the whole machine M that recognizes the language. Now you can check with some examples, both with strings that should be accepted by your machine and strings that should be rejected by your machine. Let's try 1010. Starting from A, without reading anything, I can go to B and E. So that A, B, E should be the states that I can reach without reading anything. Starting from there, I will consume each symbol in the string one by one. So from A, B, E, if I read a 1, I can reach B and F. Because from B, after reading a 1, I stay as B. And from E, after reading a 1, I reach F. So this BF is the set of states that can be reached from the set of states ABE after consuming a single 1. Of course, you need to take the closure of this B and F because this machine is an epsilon NFA. But in this case, the closure of B and F is just B and F. Remember, the closure of a set of states is the set of states that can be reached from the starting states B and F following 0 or more epsilon transitions. Now from B and F, reading a 0, I can reach C and F. C is reached from B and F is reached from F. You have to read a symbol 0. You can't say, I stay at F because I'm starting at F. That's not the reasoning. The reason that I stay at F is because after reading a 0, following that transition, it reaches F. Now from C and F, after reading a 1, I reach C and G. C is reached from C and G is reached from F. Now the final symbol, from C and G, after reading a 0, I can reach D and G. D is reached from C and G is reached from G. In each step, you need to take the closure of the resulting states. And for this special machine, for all my steps here, the closure are just themselves. Now we check, I have read all the symbols in this string. I check the resulting states. I can reach D and G. And D and G are final states, so I should accept the string. For the machine to accept a string, you only need to check the resulting states. If the resulting states contain at least one final state, then the machine should accept this string. Now let's check another example, 1101. This should be rejected because I have less than 2 zeros and I have 3 ones. Let's check the computation. Still, we start from A and take the closure of A, which is ABE. That means without reading any symbols, the machine can reach ABE. Now we'll read the first symbol, 1. ABE can reach BF by reading a 1. B is reached from B and F is reached from E. And we take the closure of B and F, which is B and F. Now the second symbol, we read another 1. So from B, we reach B, and from F, we reach G. and we take the closure of B and G, which is B and G. Now the third symbol, 0. After reading this 0, we can reach C and G. C can be reached from B, and G can be reached from G. Now at this stage, some people say, oh, this G is the final state, so I should accept this string. This is not true, because I have not consumed all the symbols of my string. So when you check the final states, the resulting states, you should check the resulting states after reading the whole string, every single symbol in that string. So we have one more symbol to read, that 1. So from C and G, I can only reach C. C is reached from C. But from G, since there's no transition for that 1, so this G can reach empty set. We take the union of C and empty set. The resulting state is just C. And we take the closure of C, which is also C. And C is not a final state. So the machine should reject this string. Following the same procedure, you can check the other strings and see if they are accepted or rejected. Now that we have constructed an NFA, let's convert this NFA to an equivalent DFA. To do that, we need to specify the 5 tuple for this new machine, DFA. The set of states of this DFA is the power set of the set of states of that NFA. So each state of this DFA is going to be a set of states in that NFA. The starting state of this DFA is going to be the set of states that can be reached from the start state of that NFA by just following epsilon transitions. And the final states of this DFA is going to be each state of this DFA that contain at least one final state in the NFA. Now is the big part, the transition functions. Let's do that by running an example. In principle, if you want to compute the transition function for this DFA, you need to compute the transition for each state in this DFA. But since many of the states in this DFA are not reachable from the start state, the procedure I show now is going to be considering all the states that are reachable from the start state of DFA, and I'll omit those states that are not reachable. So we start from the start state, which is the states that can be reached from the start state of the NFA by just following 0 or more epsilon transitions. So in this case, the start state of this DFA is going to be A, B, E. Now we need to read a symbol. For the alphabet, we only have 0 and 1. So we only need to consider these two cases. If your alphabet is 0, 1, 2, then in this table, you need to consider those three cases, 0, 1, 2. All right. So from ABE, after reading the symbol 0, I want to have the set of states that can be reached from ABE by consuming a single 0. So we first check the resulting states by reading a single 0 from ABE. From A, I can reach empty set because there's no transition for 0 from A. From B, I can reach C. And from E, I can reach E itself. So the resulting states that can be reached by consuming a single 0 is C and E. Now we need to take the closure of this C and E. That means if we can reach this C and E, if there are any epsilon transitions out of these states, then we can also reach those states by consuming nothing. In this case, the closure of C and E is C and E itself. Similarly, now I want to consider the symbol 1. From ABE, I want to check the resulting states by consuming this single one, and then take the closure of those resulting states. So from A, I can reach nothing from 1 because there's no transition for 1. From B, I can reach B itself. And from E, I can reach F. So the resulting states are B and F. Now we take the closure of B and F. Since there's no epsilon transitions out of this B and F, the closure of B and F is just B and F. Alright, we have finished the first row, the first transitions for state ABE. We reach the states CE and the state BF. These two states are new states, and they are reachable from the starting state. So I should put these new states to the left column and consider what we can reach starting from them. Now we start from CE. From CE, after reading a 0, I can reach DE. D is reached from C and E is reached from E. Then we take the closure of DE, which is DE. Similarly, from CE, we read a 1, then we can reach C and F. And we take the closure of CF, which is CF. Now these states, DE and CF, are new states. So we need to put these new states to the left column. Those states are reachable from the start state. Now consider B and F. From B and F, reading a single 0, I can reach C and F. C is reached from B and F is reached from F. So we take the closure of C and F. That will be C and F. You can check the other transitions. This is the procedure. Starting from a state in the left column, reading a symbol, either 0 or 1, you compute the resulting states that can be reached from each state in that set. Then you take the closure of that resulting states. That will be the set of states that can be reached from your start state by reading a single symbol. There is a special case I want to tell you. For example, from that BG, if I read a single symbol 1, I can reach B an empty set. B is reached from B, and the empty set means it can't be reached from G. If you check that G, there's no transition for 1. So you take empty set there. Remember, you have to consume the symbol first, then following the epsilon transitions. So for this example, even if there are epsilon transitions out of this G, the resulting state by reading a 1 from that G is still empty set, because I have to consume a symbol first. I have to get the result states, and then I take the closure of the result states. You do this computation every time you have two states. After reading the symbol 0 or 1, you check if they are new states or not. If they are new states, just put them in the left column. You do this computation until you have no new states. That means you have finished the computation. For example, the last state is D. From D, after consuming a single 0, I stay at D and take the closure of D is just still D. And after reading a 1, I also stays at D and take the closure of D, still D. And there's no new states left in the left column. So that's the end of the computation. Now I should draw the diagram according to this transition table. But before we draw the diagram, you need to specify the start state and the final states. The start state is easy. that's the first state, ABE. And the final states, remember each state in this DFA is a set of states, right? So in that set, if you can find a final state in this NFA, then that state, that set, should be a final state for this DFA. For example, we have 6 final states here. The first one is DE because D is a final state in that NFA. And the second one is BG because G is a final state of their NFA. Why we consider these states as the final states of DFA? Because this states means if I consider DE, that means this state DE is reachable from ABE. Following some transitions, I can reach this D and E. If you consider the computation of NFA, that means I have 2 branches that can reach D and E. One branch reaches D and one branch reaches E. So long as one branch can reach a final state, this machine should accept this string. So after consuming this string, I can reach D and E, and D is a final state, so I should accept this string. That's why we put any states that contain a final state in this NFA to be a final state of this DFA. Now we draw the diagram. The diagram has 12 reachable states. The DFA has 7 states. So if we do the complete computation of the transition functions, we should consider 2 to the 7 states for that DFA. That's a lot. The procedure I just talked about only follows the reachable states. Eliminating those unreachable states does not have an effect in the computation of this machine. Because they are not reachable, I will never use them by consuming any string. Alright, the diagram contains 12 states, and 6 of them are final states. By the way, the diagram contains all the information for the machine, all those 5 tuples. Each node here is going to be a state. Each arrow here is going to be a transition. And we have the start state, and the final states are double-circled. This is a compact way to describe a DFA or an NFA. Now consider the language. The language is the set of strings that contains at least 2 zeros or exactly 2 ones. If we analyze this machine, the first column of the states, those states means they have consumed no zeros at all. And the second column, those states means they have consumed a single zero. And the third column, those states, they have consumed 2 zeros. So they have satisfied one requirement. They should be accept states. Now we consider the rows. The first row of states, those states have consumed no ones at all. And the second row, those states means they have consumed a single one. And the third row, those states, they have consumed exactly 2 ones. So from that state, BG and CG, if they consume more ones, they will reach B and C. B and C are not accept states because they have consumed more ones than needed. But they can still transition to accept states if they can consume at least 2 zeros. This machine is a simplified version of the complete DFA constructed from the NFA by eliminating those unreachable states. But we can further simplify this machine. If you check those third column, those 4 states are all accept states, and the transitions between them only stays in them. There is no transition from them to a non-accept state. So if I reach any of them, I stay in final state. What I do is I can combine them into one single state. Once I reach this state, I will stay at this state. And this state is an accept state. So I can replace these 4 states by a single state. And after I reach this state, I can read any number of zeros and ones. Now we have talked about, given a language, we can construct an NFA that recognizes this language and converts that NFA to a DFA. There are many ways to construct NFAs given a language. Now I will show another way to construct an NFA that recognizes the same language, the set of strings that contain at least 2 zeros or exactly 2 ones. Now I want to partition them into 4 parts. The first part is the string starts with a 0 and contains at least 2 zeros. The second one is the string starts with a 0 and it contains exactly 2 ones. The third is the string starts with a 1 and contains exactly 2 ones. And the fourth is the string starts with a 1 and contains at least 2 zeros. So if I start from A and I read a 0 and I want to read at least 2 zeros, what I do is I go to B and read another 0 and reach E. E should be an accept state because I have read at least 2 zeros. And if I read a 1 from B, I should stay at B because the number of ones doesn't matter in this branch. And from E, since I have satisfied the property at least 2 zeros, I can read any number of zeros and ones after that. The second one, I want to start with a 0 and I want to read exactly 2 ones. What I do is I read a 0 and I reach this D, and from this D, I should read a 1 and reach that C. C means I have read exactly 1. And from that C, I want to read exactly 2 ones. What I do is I can read another 1 and go to F, or I can read a 0 or any number of zeros and then read a 1. The difference here is I have 2 consecutive ones or I have separated ones. Alright, the third one is I start from a 1 and I read exactly 2 ones. So if I read a 1, I should go to C. That means I have read a single 1. And then I consider I read the second one right after this one, or I can consume some zeros and then read a 1. The fourth one is I read a 1 and then I read at least 2 zeros. So after reading a 1, I reach C and I read 2 more zeros to reach this I. And from I can read any number of zeros and ones. This is another way to recognize the same language. But I personally think if you have an OR in your language, the natural way is to construct 2 machines and then use epsilon transitions to take the union of those 2 machines. Alright, now let's prove a closure property of regular languages. Regular languages are closed under union, intersection, concatenation, clean star, and now we're going to talk about reverse. We want to prove if a language L is recognized by some finite state automaton M, that means L is regular. Then we want to prove this LR is also accepted by some finite state automaton. That means this LR is also regular. What is this LR? LR consists the set of strings of L reversed. For example, if ABC is in L, then CBA is in R. So LR will have the same number of strings as L, but each string in this LR is the reversed string of this L. This LR should contain exactly that many strings as L. We do this proof by construction. We know that L is recognized by M. So this 5-tuple of M, Q, sigma, transition function, the start state Q0, and the final states F, they are given to us. They are known. We can use this machine, these 5 tuples, to construct the new machine M prime that recognizes the language LR. How do we construct this new machine? Remember, when you start from a start state of this M, you read the string, for example, ABC. If this string is accepted, after reading this string, the transition function will take you from the start state Q0, then the next state, then the next state, and that final state is an accept state of this M. That's why you accept this string. Now I want to accept the reverse of this string. A natural way would be, I have this path from the start state to that final state. And this path consists transitions for each symbol in my string. Now I have the reversed order of my string. If I can go from that final state and go backward by reverse all the directions of the transitions in my previous path, then I should reach the start state and consume exactly those many symbols as my string before. So if I reach the start state, I should stop here and I should accept, because I have read all the symbols in reversed order. So that's the idea. I start from the final states and go backwards and see if I can reach the start state of this M. To do a proof by construction, I first need to construct this new machine using information of the existing machine. So I need to specify the 5-tuple for my new machine by using information using those 5 tuples from my existing machine. The idea is to reverse the directions. But remember that for an NFA, we can only have a single start state, but we can have many accept states. So if my original M has multiple accept states, by reversing the order, I should take those accept states as my start state. But there are many of them. Which one should I choose? In principle, all of them should be start states. But by the definition of NFA, we can't have multiple start states. But luckily, we have epsilon transitions. So we can add a new state, start, to this machine and add epsilon transitions from this start to my final states in N. So I can start from multiple places, non-deterministically. So the set of states for this new machine, M prime, should be my original states from M and this new start state. And the new alphabet is exactly the same alphabet, because I should accept the strings with reversed order. I should not accept any strings that contain symbols outside of this alphabet. And the start state of this new machine should be that new state, start. And the final states of this new machine should be Q0, because from the final states I reach backward. If I can reach this Q0, that means I have consumed all the symbols. Now for the transition function, remember we need to reverse the direction of each transition in my original machine. For each state, for each symbol in the alphabet, we need to define a transition for them. So if I have a transition from R to P by reading the symbol A in my original machine, I need to reverse that direction. That means I can reach R from P by reading a single symbol A in my new machine. And I do this for each state and each symbol. That's not enough for this transition function because I have a new start state. I also need to define transitions for that start state. And this principle is, from this new start state, I should be able to reach any of the original accept states by reading nothing. So I add epsilon transitions from start state to those final states. Now that's a complete new machine. In the original machine, the computation starts from Q0 and following directions to reach final states. And now my new machine starts the computation from this start state. And by following epsilon transitions, it can reach all the final states in that M, and from there they can reach backward to Q0. This is the construction of this new machine. But this is not a complete proof. A proof by construction has two parts. First, you construct the new machine by using information of the existing machine. Second, you prove this new machine does exactly what you want it to do. In this case, I want to prove this new machine M' recognize this LR. To do this, we need to prove two parts. Lm' is a subset of LR, and the second part, LR, is a subset of this Lm'. Let's do the first part first. To prove Lm' is a subset of LR, what we need to do is, for any string in this Lm', we need to prove this string is also in LR. So we start with the premise. Suppose this W is in Lm', and we express this W as M symbols from Y1 to Yn. Each symbol is a symbol in the alphabet. Alright, by definition, W is in Lm'. By definition, this W should be accepted by this M'. So that means there exists a sequence of states. Start R1, R2, Rm in Q' that satisfies these three conditions. The first condition is this R1 is a member of the final states. Remember, we can start from that start state. Following epsilon transitions, we can reach any of the final states of this M. The second condition, this sequence of states corresponding to transitions. For example, if I am at Ri, I read the symbol Yi, then I should reach the state Ri plus 1. That means if I'm at the current state in the sequence, I should be able to reach the next state in the sequence by reading the symbol. And also, from that start state, following epsilon transitions, I can reach this R1. And third, my final state in the sequence, Rm, should be Q0, should be in an accept state in my M'. So that means this W is accepted by this M' by following the transitions from start to R1 to R2 all the way to Q0. Now this is given to us because we assume W is accepted by this machine M'. Now we need to connect this computation to the computation of M. So by definition of this new transition function, we know that we can reverse the order and get the transitions in N. So if I'm at the state Ri plus 1 and I read the symbol Yi, I should reach the state Ri. So the transition becomes a start from Q0 after reading those symbols ym minus 1 backwards. I should reach this state R1. And this R1 is a final state, right? So that means this WR, which equals ym minus 1, y1, this WR is the reverse of W. By definition, this should be accepted by this machine M because we have found the sequence of states, the sequence of transitions that can read this string symbol by symbol from Q0, the start state of M, and reach R1, the final state of this M, by consuming the whole sequence of WR. So we know WR is in L. By definition of LR, we know that the reverse of WR, which is W, should be in LR. So by now, we suppose W is in LM prime, and then we reached a conclusion that this W is in LR. By doing this, we have proved that LM prime is a subset of LR. Now let's consider the other direction. LR is a subset of LM prime. What we need to do is prove that for any string in this LR, this string is also in LM prime. So we start with the premise again. Assume this W, Y1, Y2, Ym is in LR. By definition of LR, I can construct a new string, WR, which is Ym minus 1 all the way to Y1. This string should be in L. Alright, so this WR is in L. So by definition, this WR should be accepted by the machine M. That means there exists a sequence of states Rm minus 1 all the way to R1 that satisfy these three conditions. This Rm is Q0, the start state of M, and this R1 is a final state in M. And this sequence of states corresponding to a sequence of transitions. From Ri, if I read a symbol Yi, then I can reach the next state, Ri minus 1. So the computation for this string is starting from Q0, consuming Ym, I reach Rm minus 1, and all the way to R1 by reading the last symbol Y1. Alright, so this is given to us if we assume the premise is true. Now we connect this computation of M on WR to the computation of M prime on W. By definition of the transition function of M prime, we know we can reverse the order of the original transitions in M. So if I'm at Ri minus 1 and I read the symbol Yi, I should reach the state Ri. So this W should be recognized by this M prime by following the sequence of transitions. From start state, I consume nothing and I reach this R1. And following that sequence of computation, I can reach this Rm, and this Rm is Q0. Q0 is an accept state in this M prime. And this sequence of transitions from start to Rm correspond to reading each symbol Y1 through Yn. So that means this W is accepted by this machine. By now, we assumed W is in LR and we reached the conclusion W is in LM prime. So we have proved that this LR is a subset of LM prime. But doing these two parts, we have proved that this Lm prime equals Lr. That means M prime recognized language Lr. By now, it's the complete of the proof.